So here I'll give you a brief demo of how to use the oscilloscope and how to look for the signal and then measure its characteristics using the oscilloscope. So this is your oscilloscope, and the device at the bottom is the function generator, and there are already videos which will demonstrate how to use the function generator as well as the digital multimeter. And in this lecture, in this demo, we'll be mainly focusing on the oscilloscope. Okay, so the first thing that we need to do is switch on both the devices. So at the back of these, you will find that 220 volt power connector. So you connect the cable to it, and then the other end into your line socket, and then using the power button, which should be marked somewhere. So for example, in this model, the power button is at the lower end. In some of the oscilloscope models, there would be a power button at the top here. Right? Okay. So we switch it on, and now when you want to see the signal, so your oscilloscope is a device, is a measurement device, just like your digital multimeter, and it can be used. It's primarily used to analyze AC signals, but it can also be used to analyze the DC signals. So all the measurements that one could do with a digital multimeter in terms of voltage measurements can be performed using a digital oscilloscope also. It's also called sometimes as DSO, right? And that's because if you can zoom in here, then or you look at your oscilloscope at the somewhere here, there is a sticker which says digital storage oscilloscope. So it's a digital device, it's an oscilloscope, so that it can give you a trace of the AC signal waveforms, and these particular models, we can also use them to store the data of the signals that we are analyzing, and that's why it's called a DSO, or a digital storage model, right? Okay, now the first thing to look for is what is the input, or where do we give the input to the oscilloscope, right? And again, it's a measurement device, so one has to keep in mind that it will always have only input. It's not going to give you any output, right? So so you're not going to take a signal out of this. You are only going to feed the signal into it, and then at the display you will see characteristics of that signal. Right. Now the first thing that we need to know is where to give the input. So these models have two input channels, channel 1 and channel 2. So they are marked as 1 and 2, and correspondingly there are some control buttons. So for example, this one, this and this, so they are corresponding to channel 1, right? And as far as the trace is concerned, they have these oscilloscopes have a color display. So the inputs at these two different channels can be identified with a different color. So channel 1 will be in yellow, and that's input 1, and channel 2 is marked as blue, and that's your channel 2, right? Okay. Now what the display shows, or what the oscilloscope will do, is on the display, on the vertical axis, it will display the amplitude of the signal, and the horizontal axis is then the time. So that way, it's just like a normal graph that we plot on a pen and paper. So it gives a time evolution of the signal, and in more detail, it gives how the signal amplitude changes as a function of time. And if it's a periodic signal, if it's a periodic function, then basically you get the same pattern repeated again and again. Right? Okay. So now to go into more details of how to operate this oscilloscope, first let us define a particular signal. And this point you should keep in mind while working with oscilloscope, that it's very important. In fact, it's very important for anybody who is handling signals and who is working with signals to have at least some rough idea that what is the signal that one expects to measure, right? Because that way one can set the ranges in the display properly and see the signal in proper detail, right? So to begin, so we'll discuss this point again while performing experiments, and from our understanding of the theory, we will always be able to guess what is the output, or we will always know that for what we have made the circuit, so what is the expected output, and that way we could set the range for the display. Here what I am going to do is I am going to use a reference signal to show you how to set the oscilloscope properly, and that reference signal will be taken from this function generator. So I have a 1 kilohertz sinusoidal waveform with amplitude which is 2 volts peak to peak, that means plus minus 1 volt, right? So that's my output of the function generator, which I want to now feed into the oscilloscope and see that how a 1 kilohertz sinusoidal waveform with 1 volt peak to peak, 2 volts peak to peak amplitude looks like, right? Okay, now how do we connect these two? So if you look carefully again, the input channels, right? So they are not like a power socket or any other connector that you may have seen. These are special type connectors. These are mainly used in with coaxial cables. These are for radio frequency operations, right? Or high frequency signals. So these are called the Bnc connectors, right? So you have the inputs given through Bnc connectors. Similarly, the output of the output of the function generator is also a Bnc connector, right? Because this also generates high frequency signals, right? And the Bnc is a special type of cable which is a coaxial RF cable, so that the signals transmitted to it are to a greater extent are shielded from the outside noise interference. Okay. Now, how does a Bnc cable look? So a Bnc cable would look something like this. It's a normal coaxial cable, right? So just like your dish antenna cable, right? And at the ends of it, there will be 2 Bnc connectors. So this cable is already is provided to you in the box. So you can identify this, take it out. And now what we'll do is we'll connect one end of this cable to the function generator output and the other end to the oscilloscope input. So let's feed into channel number 1, right? And that's it. So I have made the connection. Now, as long as my function generator actually is giving me an output of 1 kilohertz 2 volts peak to peak sine wave, I should be able to see it on the monitor, right? But we do not, because we have not yet set the parameters correctly. So now let's go over these steps, and basically these are the primary steps that one needs to know to see a signal. Okay, so the first thing that we need to know always, and I would recommend that you, if possible, you write down these steps, so that and then every time you work with oscilloscope, to begin with, you go over these steps, and slowly you will be habitual of doing it. Okay, so the first step is to know on which input we are giving the signal. So for example, here, if you have only single one, then it doesn't make a difference. But if you have more than one signal, then you need to identify at which channel which signal is going. So here we are giving the signal to channel 1, right? And what that means is, if the input is going at channel 1, then the display should be set for channel 1 in the proper range, so that we can see the signal. Okay, so now what I'll do is, let me sort of focus on the oscilloscope now rather than the function generator, because we are not discussing the how to operate the function generator, but the oscilloscope, right? And now let's go a bit closer to this, right? So now what we have here is, on the display you can see some things written on the 2 sides, right? And this is then the display screen. So the things in yellow, marked yellow, will be corresponding to channel 1. Things marked colored blue will be corresponding to channel 2, right? Okay, so the signal is at channel 1. So first what we have to do is, we have to identify, we have to set the range properly to see that signal. And by range, I mean, let's say the vertical scale. So the vertical scale is basically showing you the amplitude or the voltage value of the signal at different times, right? Because it's a time varying signal, and the vertical scale is graduated, so you can see these different boxes, and and the boxes are also graduated with dots. So this sets a scale, and that scale is shown here, right? So this is, for example, here it's 500 millivolt. What that means is, each of this square box on the vertical scale corresponds to an amplitude value of 500 millivolt. So if this central crosshair corresponds to, let's say, 0. So if this is 0 volt, then this is 500 millivolt. This is additional 500 millivolts, so that's 1 volt. Additional 500, so 1.5 volts, and then 2 volts. Similarly, 0, negative 500 millivolts, negative 1000 millivolts, negative 1500 millivolts, and negative 2000 millivolts, or minus 2 volts. Right? So that's the scale. And now we have to, and we can change this scale using the course and the knob to change volts per division. Right? So this graduated scale is divided into volts per division. Each block corresponds to this many volts, and we can change that, right? And now what we have to do is, so we have to first find out what is our signal amplitude, what is the expected signal amplitude. We expect a signal amplitude of plus minus 1 volt on either side, right? So that means this scale, which is set at 500 millivolt, is probably okay. I can go lower. I can go to, let's say, by turning this clockwise or anti-clockwise. If I turn it anti-clockwise, then this goes to 1 volt. I can turn it anti-clockwise and then go to 200 millivolt. So I can change the range this way. But 500 millivolt seems fine, because overall, on the vertical side, the display gives me a total change of plus minus 2 volts, and a plus minus 1 volt signal can be easily seen on this. Okay, so the vertical scale seems to be in order. Now what about the horizontal scale? So horizontal scale represents time, right? So again, the cross wire tells us 0 of the time, so t equal to 0, and then on either side you have forward time and backward time, in the sense that given a reference, you can see if the signal is, if you want to measure the signal after that t equal to 0, or what is the state of the signal before t equal to 0. So that's why t equal to 0. And then again, the horizontal scale is also graduated in the same way. So 1 block, 2 block, 3 block, 4 block, and so on. And the division of each block in the horizontal side is given as here, right? So that's here it shows 250 microsecond. That means the total time that one can measure is, basically one has to simply count the number of blocks. So 1, 2, 3, 4, 5, and 5 on the other side. So total 10 blocks multiplied by 250 microseconds. So that gives us about 2.5 milliseconds. So we can represent a signal, or the state of signal, how the signal changes its amplitude in a given 2.5 millisecond time period, right? Or time slot of time block, right? Okay. Now, where is it important? How do we, what value should be set for our purpose? Now that is determined by the time period of your signal, because normally what you want is, you want in the display at least couple of cycles, couple of full cycles of the signal to be shown, to to know its characteristics as a whole. Right? So for that, so for example, if I have 1 kilohertz signal, that means its time period is 1 millisecond, right? And if I want to see, so in 1 millisecond I'll have 1 full cycle, and if I want to see 2 cycles, then my time window should be at least 2 millisecond wide, right? So here from negative to positive, it's about 2.5 millisecond wide, right? So that's sufficient. In fact, we'll be able to see the signal at least 1 full cycle here, right? So that's also okay. So the ranges are fine, right? And what we'll see is, we are still not seeing the signal, right? So what else? One of the important things that, and okay, so before moving how to get the signal here, let me just show you that how do we change this time scale, and that's using this knob. So it's marked time per division, and that's in the horizontal direction. Again, what you can notice is, for the input we have 2 channels, so we have 2 corresponding knobs which can change the volts per division on the vertical side. But on the horizontal, since both the signals are measured with the same time reference, we only have 1 knob. So the time scale is same for both the signals. Okay, so that's fine. And you are still not seeing the signal. That's because there is something else which needs to be set in these oscilloscopes, and that is called the trigger, right? So you can see it here. And in different models, it could be placed at a slightly different location, but mainly in this area. So the trigger, and the trigger is basically, so what happens is, your signal is actually it's a continuously varying output, right? And it's moving continuously ahead in time, right? Whereas the oscilloscope has a limited screen size, right? So you want to see the signal there. So what it does, it keeps refreshing the data continuously, right? However, if the reference at which it refreshes the data is not correlated with the periodic signal itself, with the periodicity of your signal, then what will happen is you will keep seeing fluctuations here, right? And I'll show you that how do we get that. But you will keep seeing fluctuations here, and you will not be able to see a steady state waveform. So the trigger that way needs to be set properly, and the way to set the trigger is that, first of all, depending on which input you want to see. So suppose I want to see this input 1. So the trigger has to be set at channel 1 because the input is given at channel 1. And here you can see the trigger. So you can see a small T here, and alongside it, it's set in channel 2. That means right now the trigger is set at channel 2. However, there is no signal at channel 2. So that's why we are not seeing any display. The oscilloscope is not refreshing in correlation with the input signal. So now we have to first change the trigger to channel 1. And the way to change it is you go to the trigger menu. So on the trigger side, you will have different options. So this is for changing the level of the trigger, this knob, and then you have a menu and then single and fourth. So we'll see how it does. So what you do is you press on this menu, and on the screen you will get the parameters. So these are the trigger menu parameters. So trigger, now what is the type? Type H, right? And you can now you can try this out. So after looking at this video, you simply switch on your oscilloscope and try out these different things. So you can see what different types it can have. So the type right now set is edge. It can have a pulse, right? So normally if you have a periodic signal, then you select edge type. But when you have pulse signals, you select the pulse. Right? You can have a video, and so video is basically a continuous trigger, but it's very hard to then set it to the same periodicity as that of the external input, right? So anyway, and you can see that as soon as I set the oscilloscope internal trigger, then there's something coming. But that's what will happen when you don't have a proper trigger set, that you will see this periodic waveform, but its periodicity is not correlated with the refresh rate of the oscilloscope, and that way the signal appears here and there on that horizontal scale, right? Okay, so for our purpose, we want it to be set at edge. So you press it again, and now it's at edge. Now the source has to be, we don't want the internal reference source, we want the external input source, and that has to be channel number 1. So let's select the source by pressing this button here, corresponding button. So for the top one, there is a top one, for the next one, next one, next one, next one. So these parameters are correlated with these buttons. So you go for channel 2, and then you press here. So it will show you external. That's for the third input, which we are not discussing, the external input. You can also trigger the oscilloscope by external reference, right, which is not your input. But right now we will just trigger it on the input. So source, not external, not line. We do not want it to be triggering again internally. It triggers using the 50 Hz line frequency, but channel 1, right? So the source is channel 1. If I press it again, I'll go source as channel 2, right? So, and then external, then again line, and then again channel 1. So this is a cyclic parameter button, which you can just keep pressing till you get the correct parameter. And as soon as we have selected the source as channel 1, you can see that now we have a steady state waveform, right? It's not something that is frozen in time. It's because the input is basically 1 kilohertz sinusoidal waveform, and it's continuously going forward in time. However, the refresh rate of the oscilloscope now matches with the periodicity of the signal, right? So that means every time the same part or the same region of the waveform is displayed on the oscilloscope, and that's why we see it as a stable signal, right? Correspondingly, you also see now a blue flat line which corresponds to channel number 2, right? And if there was a signal present here, then that signal will also be shown here in reference to the trigger of channel 1. However, right now there is no signal, so you won't see it. Now, Another functionality that this provides you is, suppose you are only working with a single input, so you don't want this blue line to appear all the time. It might lead to distraction. So what you do is you press this blue button, right, and couple of times, and then you can switch off the channel. So if you look at here, channel 1 is covered in a bright dot, so that's an active channel. Channel 2 is just the number without the bright circle around it, so that's a deactivated channel. If I press it again, I can activate the channel, and again then I can see its state here, right? Okay, so for time being, I'll just deactivate it so that we can just focus on the input signal, right? So this is my input signal. I can move this up and down, so I can set the reference for display. Again, mind you, whatever we do with the oscilloscope is not going to change the signal. It's just going to change the way we are looking at the signal, right? Okay, so what we can do is on this display side, on the vertical side, we can move it up and down. So using this knob corresponding to channel 1, so I can turn it around, and you can see what changes here is this mark. So this mark tells us where is the 0 amplitude or 0 volt reference for the signal that I am looking at, right? So for channel 1 and similarly for channel 2. So this is the 0 mark for channel 1, and if I move it up, you can see the the display moves up. I can move it down to say the display moves down, and similarly I can just bring it at the center. So this is used to basically fit in the entire signal to use the entire display range, right? Okay, so this is to be used. That's done, and now what we can do is we can try to see the amplitude. So we can change the scale, right? So if I change the scale to 200 millivolts, now with 200 millivolts, the display range becomes 0, 200, 400, 600, 800. So maximum on the positive side, it can show 800 millivolts. Similarly on the negative side, and the result is obvious that now my 1 volt peak signal is not fitting in here, right? Okay. So that's how you fiddle with the range. So if you know the range, so for example, what can happen is, suppose by mistake, your oscilloscope is set in this vertical scale, which is 20 millivolt. That means maximum you can see is about 80 millivolts amplitude signal, whereas the signal you are giving is 1 volt amplitude. And then what you will see is, you will see something like this, and then you cannot make sense of it. You will think that I was trying to give a sinusoidal waveform, which should have looked like a sine wave, right? But it shows me something, these vertical lines which are jumping here and there, right? There's nothing wrong with the input signal. In fact, there's nothing wrong with the measurement also from the oscilloscope. What is wrong is we are not looking at the correct region. We are only looking at a very, very small portion of the signal because our scale is not set correctly. So we set the scale correctly to 500 millivolts, and now it's a proper sine wave, right? Similarly, on the other side, the scale could be set at a very high value, such as 5 volts, and then that 1 volt variation will look very small, and there's not much information that will be visible by setting such a scale, right? Okay. Now the thing is that this oscilloscope will typically have a range maximum scale of 5 volts, right? Because these oscilloscopes are again small signal devices, so the input should never exceed 5 volts. I mean, of course, not really 5 volts, because 5 volt is the scale, so 5, 10, 15, 20, so not more than plus minus 20 millivolt. In fact, the function generator will also not give you more than 20 millivolts peak to peak signal, right? So that these two are compatible with each other. But just as a precaution, never give more than 5 volts DC to this oscilloscope, and do not try to connect your normal AC line signal to this oscilloscope, because that's about 220 volts, and that will simply destroy it, right? So it will destroy the input channel, and once the input channel is destroyed, the oscilloscope is useless. Okay. So let's bring in this one to the correct range. So again 500 millivolt. Similarly, we can see how many cycles we want to look for the signal. So for example, here I have 1 cycle and then 2 cycles. So 2 cycles shown completely, and then some quarter cycle here on the either end. I can change the time scale. So I can go either either higher. So that means each division now corresponds to 500 microsecond. So I'm able to see more cycles here. I can go higher and higher, and then so if you are not in the proper range again, then basically you will see many more cycles than you can get information from, right? Or you can lower the range. So for example, here now I'm at 100 microsecond, so the total will be about 1 millisecond, and that's exactly fitting with one time period or one full cycle of my waveform. So I can see it like a one full waveform, right? And now if suppose there is some interesting feature happening at the zero crossover point, then what you can do is you can change the time scale around here and then see that thing. So for example, now we are only looking at about 100 millisecond part of that zero crossover in the waveform. So whatever small features are happening here, in case my circuit develops such kind of signals, then we'll be able to monitor it and measure it more accurately. Okay, so let's just go back to 250 microsecond, and that gives me 2 cycles of this, right? So the important thing to note down while measuring input signals: know at which terminal, which channel you are giving the input, channel 1 or channel 2. Depending on that, set the voltage scale, the vertical scale, volts per division properly, so that your entire signal fits in the display window. Set the time scale properly, so that at least couple of cycles fit in the display window, so not too many, not too less. And set the trigger using the trigger menu to the input signal at which you want the oscilloscope to be triggering, right? Okay. Another important feature that one should keep in mind with this trigger is that trigger level, right? So this knob above the menu, and the trigger level is basically when you move it, it will be shown somewhere here. So for example, on the right hand side, so on the left hand side with this 1 and that arrow, that shows the DC level, the reference level of your signal. So where the 0 is set, the right arrow, this small arrow here, this shows what is the reference value, the voltage value at which the oscilloscope triggers. So at which, basically the oscilloscope measures the signal, and then you need to tell it some reference that in terms of measurement and in terms of display, that at what should be the amplitude of the signal, so that you will treat it as a signal and not noise, because it could happen that you have a signal which also has a noise and you only want to see the signal but not the noise, right? So that's called the trigger level, which is then shown by can be controlled by this knob, right? So for example, here if I move this knob clockwise or anti-clockwise, then what you start seeing is you start seeing a trigger level here, right? So if I don't do anything, then that information is not there. But now look at this lower end of the screen of the display. If I move the trigger level knob, then you start seeing this trigger level, and for example right now it's 80 millivolt. I can change it, it's 180 millivolt, and this arrow on the right side can be moved up or can be moved down, right? So that's a trigger level, and it has to be also set properly, because what happens is the oscilloscope display will be also synced to this trigger level. So for example, when the trigger level, right now it's set to 0. So when the trigger level is set to 0, that means this cross wire will be matched with the 0 crossing of the signal. So here you can see that at the cross wire, the signal is also exactly 0. And then it rises, falls, crosses 0, goes to that one cycle, and again a previous cycle, right? If I move this signal level to, let's say, 100 millivolt, a trigger level to the 100 millivolt. So here, right, something here, trigger level is 100, and you can see it's moved here. There is a small shift of the signal. You cannot see it because 100 millivolt is still much smaller, but there is a small shift, and what we can do is we can try to go it substantially higher. So let's say 500 millivolt. So I'm not triggering, so refreshing my display when the signal amplitude crosses 500 millivolts, right? And now you can see that this crosswire does not match with the 0 crossing of the signal. Rather, it matches with the value when the signal, the amplitude actually crosses 500 millivolt, right? So that's how, that's what the trigger does in terms of display. But more importantly, if, for example, if the trigger is set at more than the amplitude of the signal, then you will not see the signal, right? So for example, what I can do is I can switch off channel 1 and then reactivate it, and now you don't see the signal. Your vertical range is fine, your horizontal range is fine, your trigger is set to channel 1, right? And yet you don't see the signal because the trigger level is not set. The display will now only refresh when the input signal crosses whatever is this trigger level value. So this is about 1.2 volts. So if the signal never crosses more than 1.2 volts plus 1.2 volts, you will not see anything because the oscilloscope is just not refreshing. It's not showing you whatever is being fed to it, right? And will my signal cross 1.2 volts? No, because I have given it 1 volt peak amplitude signal. So it will never cross 1.2 volts, and that's why I am not seeing it. So again, what we need to know is, if the amplitude of my signal is 1 volt, that means my trigger should be less than 1 volt, right? So the trigger level I'll now set at less than 1 volt, and as soon as my trigger level is less than 1 volt, I'll start seeing the signal. And then depending on how I want to set it, for when the input signals are perfectly periodic, it's always a good, and without much noise and all that, it's always good to set the trigger level at close to 0. Slightly higher or lower than 0, but around that mark, so that you never miss or you never lose your input, right? Okay, so that's about the trigger level. So more or less that finishes off how to work with the oscilloscope. There are a few things that again I'll just repeat again so that you can go over them again and again. Know what is the signal in terms of what is the amplitude and what is the time period, and then see that your oscilloscope display is set in the proper range. Know at which input you are giving the signal, channel 1 or channel 2. If it's at channel 1, then set the parameters for channel 1 accordingly. If it's at channel 2, then set the parameters for channel 2 accordingly. What parameters? The amplitude scale or the volts per division. So set them so that you can see the full signal inside the vertical window. The time scale, so that you see at least couple of cycles of the signal inside the horizontal window, and set the trigger level to the correct input channel and to the correct value. And the trigger level value for periodic signals could be can be placed close to 0 without worrying too much about it. Okay. So these are some of the small things, some of the main things while looking at signal. And then depending at what time and who was the previous user, your oscilloscope has many more functionalities, and there could be other things which may not have been set properly. So I'll go over one of these, and then rest I'll cover during the experiments itself, right? One of these is, so when you press this channel menu, you can select different channels by selecting channel menu by pressing this button, and what you get is some channel parameters listed down here. Another important thing that one has to look for is coupling, right? So the coupling is basically which way the oscilloscope measures the input, right? Now coupling has 3 modes. One is DC, which is shown as a flat line, right, as a straight line. So that's DC coupling, and normally you should always remain in DC coupling mode, right? Because in DC coupling, the oscilloscope is able to measure DC as well as AC. In AC coupling, it only measures the AC component, does not filters out the DC component, and then there is a ground coupling in which it simply shows the reference level, it does not measure anything, right? So anyway, you can select the coupling by selecting the channel menu and then the top button which represents coupling. So if you press it once, so right now it's in DC. If you press it once, it goes into AC, right? So now it's AC coupled, right? And if I press it once more, then it goes into ground, and in ground mode, it will not show you the input signal. It will basically simply show you the ground level. So this is the symbol for that. The channel 1 is basically grounded, so no input is going inside. And then I can again select this as a normal AC coupling, right? And I should be able to get the signal. Okay, so channel 2 was off, so I'll just switch on the channel 2, and then you see the channel coupling. I think there is some okay. So again, this kind of distortion that you saw just now, if you had noticed, is because of the instability in the cable, right? In the coaxial cable that was connected. If it's not properly fitted, if it's loose fit and all that, then it might lead to this kind of instabilities, right? Okay. So just to go once more on the coupling. DC coupling, you will see the signal. AC coupling, I mean in this case you will see the signal because it's an AC signal, so nothing changes. And ground coupling, you will not see anything, and then again we will switch back to DC coupling. So this is the another important point to keep in mind, that if by doing all that previous things, amplitude, scale, time scale, trigger level, trigger channel, if with all this also you don't see the signal, then maybe look for the coupling, and you might find that the coupling is not set according to the signal, so change to that. And normally a DC coupling is the best to start with, unless you want to filter out the DC component of a given signal, right? So we'll touch upon that later. So that is another important thing. And then to end this demo here, right, so that you can start trying out these things for by your own. When you want to give signal from function generator to oscilloscope, you use this Bnc cable, right? While making circuits, basically we are going to make circuits on the breadboard, so we are not going to use we will not have these coaxial connectors all the time available on the breadboard. In fact, we will never have them. So how do we give signal to the oscilloscope, right? Now what in the packet, what you have been provided is another set of cables, right? And one of those looks something like this, right? So it's a cable which looks like this. So one end is a simple, it looks like a Bnc connector. Another end looks like this. This is called a probe, right? And it's especially made for oscilloscopes. So you have been provided two of these cables because you have two channels, so that you can attach two probes to this. The Bnc end goes to the oscilloscope, right? And now on the breadboard you can use this connector, this probe connector, to see the signals. Again, this hook is supposed to be used for the signals, right? And you should only use this hook for the signal because it is connected to the internal core of this Bnc cable, coaxial cable. The crocodile pin, this is called a crocodile pin, right? So this crocodile pin is then connected to the outer sheath or the of this coaxial cable, which is grounded. So this connection is internally grounded, right? It's actually connected to the outer covering of this connector, and that's always grounded, right? So you can never pass a signal through this pin. So if you reverse the connections on the breadboard, if you connect your signal to this crocodile pin and ground through this hook, then you will not see the signal. So keep in mind that oscilloscope measurements on the breadboard use this cable, no other cable. You may have other cables in the box, don't worry about them. Oscilloscope measurements have to be done through this probe cable, whose one end is this probe, another end is the Bnc, right? And the signal should be connected to the hook end, which is your probe, right? The crocodile pin attached with it is simply a ground connection, so connect it to the ground, right? Do not connect it to the signal end. Okay, anyway, we'll see this later on in actual circuits also, right? Okay, so that is more or less where we can start, looking at your oscilloscope. There are more things like measurement and other things, but I'll come to that later. Right? Right now, when you want to have when you see a signal here, for example, this is a signal. If suppose now I don't know what was my input and I'm given this output, I can still kind of get an idea what this output is just by looking at and reading some things of the graduated scale. So it looks like a sinusoidal waveform, periodic. So it's a periodic sinusoidal wave. What is its amplitude? So from 0, it goes 1 division, 2 divisions, and each division is 500 millivolts. So about 1 volt peak or 2 volts peak to peak. What is its frequency? So let's say it starts from 0 and one cycle is about 1, 2, 3, 4 divisions on the horizontal scale, which is 250 microsecond. So about 1 millisecond. So the frequency seems to be, so time period is 1 millisecond. frequency is 1 kilohertz. So this way we can make some rough measurements. In fact, this is the like the more common way of reading signals out of the oscilloscope, but there is a more advanced feature built in. There is a button here which says measure, right? And of course its location can be different depending on the model, but there will always be a measure button here. So by using this, one can actually make more quantitative measurements. So these are internal measurements done by the oscilloscope and shown to you so that you can take the values correctly, right? So this will come again when we perform a actual experiment, but you are welcome to now try out different modes of this oscilloscope, right? And do this. Do not worry if you lose the signal at some point, or by mistake you press something and then you don't know how to get back to the home screen. Usually these devices, when powered off, will always go into their home state, and then when you switch it on, it will come back as good as like you have not changed any settings. So in case you are completely lost, simply switch it off, wait for 10 seconds and then switch it on, right? So that would finish this display for time being, right? And you try it out. Maybe you will face some initial difficulties, but then we can go over those in one of the discussion sessions. Thank you.